Right now, somewhere in our galaxy, a city-sized sphere is spinning faster than your kitchen blender, 700 times every single second. To put this in perspective, if Earth spun this fast, every point on the equator would be moving at 9 million miles per hour. You'd weigh nothing. The atmosphere would be flung into space. The continents themselves would be ripped apart and hurled into the void. But this cosmic spinning top isn't falling apart. It's a neutron star, and it represents something that should be impossible according to everything we know about matter, physics, and the basic structure of reality itself. For decades, scientists insisted that no object could spin this fast without destroying itself. The centrifugal forces would simply tear apart any material known to exist. We were completely wrong. In 1967, Jocelyn Bell Burnell detected the first radio signals from these objects. Precise, rhythmic pulses arriving from deep space with clockwork precision. Initially, astronomers jokingly called them LGM signals, thinking they might be communications from little green men. The reality turned out to be far more extraordinary than alien radio broadcasts. These signals were coming from neutron stars, objects so dense that a teaspoon would weigh as much as Mount Everest. Spinning so fast, they challenge our fundamental understanding of what matter can endure. Here is what makes this truly mind-bending. Neutron stars accomplish this impossible feat through mechanisms so extreme. They require us to completely reimagine the nature of matter itself. They exist in a realm where the normal rules break down, where the very atoms that make up everything you see around you are crushed out of existence and replaced by something far stranger. They maintain their impossible spin through a combination of nuclear forces stronger than anything we can create on Earth, relativistic effects that literally warp spacetime and quantum mechanical properties that emerge only under the most extreme conditions in the universe. Tonight, we're going to explore one of the most profound mysteries in modern astrophysics. We'll discover how these stellar corpses achieve rotation rates that should atomically disintegrate any known material. We'll journey into the bizarre realm of nuclear pasta, where matter exists in forms that have no earthly equivalent. And we'll all uncover how neutron stars maintain their structural integrity through mechanisms so exotic they reshaping our understanding of physics itself. The implications reach far beyond astronomy. Understanding how neutron stars maintain their incredible rotation is teaching us about the fundamental limits of matter, the nature of gravity in extreme environments, and the mysterious forces that govern the cosmos at its most extreme scales. These discoveries are rewriting textbooks, challenging Einstein's predictions, and revealing that the universe operates according to principles far stranger than we ever imagined. You're about to witness the story of cosmic objects that shouldn't exist, performing feats that seem impossible, maintained by forces that push the boundaries of known physics. This isn't just about stars spinning fast. This is about the fundamental question of what happens when you push matter to its absolute limits, and somehow, impossibly, it holds together. As we embark on this journey, you'll discover why neutron stars represent one of the most extreme laboratories nature has created. Every second of their rotation tests theories about nuclear physics, general relativity, and quantum mechanics in ways we could never replicate on Earth. They are cosmic stress tests for reality itself, and the fact that they don't break apart tells us something profound about the hidden strengths woven into the fabric of the universe. Consider this. You're made of atoms, mostly empty space held together by electromagnetic forces. But neutron stars exist in a realm beyond atoms, where matter has been compressed so severely that entirely new forms of organization emerge. Understanding their stability doesn't just satisfy scientific curiosity, it reveals deep truths about what matter can become under the most extreme conditions imaginable. If you're fascinated by the extremes of physics and the hidden mechanisms that govern our universe, subscribe and hit the thumbs up button. And here is a question that will guide our entire exploration. What would happen if you could somehow slow down time and watch a neutron star surface as it completes one of its 700 per second rotations? Comment below with your best guess. I'll pin the most creative scientific speculation. The journey ahead will take us from the nuclear furnaces where neutron stars are born, through the exotic physics that governs their structure, to the cutting-edge observations that are revealing their deepest secrets. We'll explore how these objects maintain their integrity through forces that exist nowhere else in the observable universe. And we'll discover what their very existence teaches us about the fundamental nature of reality. Now, let us begin our exploration of one of the cosmos' most impossible objects and uncover the remarkable physics that allows them to spin on the very edge of destruction without falling apart. Chapter 1. Stellar Graveyard. The story of neutron stars begins with death, the violent, catastrophic end of massive stars that transforms them into objects so dense and extreme they challenge our understanding of what matter can become. To comprehend how neutron stars achieve their impossible rotation rates, we must first understand the extraordinary process that creates them and why these stellar corpses possess properties unlike anything else in the known universe. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, it faces a crisis that will reshape matter itself. For millions of years, such stars maintain a delicate balance between the outward pressure of nuclear fusion and the inward pull of their own gravity. This cosmic tug-of-war keeps them stable, burning hydrogen into helium, helium into carbon, carbon into increasingly heavy elements. But this process has an inevitable endpoint: the creation of iron in the star's core. Iron represents a fundamental barrier in stellar evolution. Unlike lighter elements, iron cannot be fused to release energy. Instead, fusing iron actually requires energy input. When the core fills with iron, nuclear fusion shuts down abruptly. In a matter of seconds, the delicate balance that maintained the star for millions of years collapses completely. Gravity, no longer opposed by the outward pressure of fusion reactions, wins decisively. What happens next defies everyday intuition about matter and space. The star's core, roughly the size of Earth but containing more mass than our entire Sun, collapses catastrophically. In less than 1 second, this stellar core shrinks from thousands of miles across to merely 12 miles in diameter. The collapse releases more energy in a single second than our Sun will produce in its entire 10 billion year lifetime. This is a supernova explosion, and it creates conditions so extreme that the very nature of matter transforms. During this collapse, electrons, the fundamental particles that normally orbit atomic nuclei, are forced into the protons that make up those nuclei. Under normal circumstances, electromagnetic forces keep electrons and protons separate, maintaining the familiar structure of atoms with their mostly empty space between particles. But the gravitational forces unleashed during stellar collapse are so immense they overcome these electromagnetic barriers entirely. The result is a process called electron degeneracy pressure breakthrough. Electrons and protons are literally crushed together, forming neutrons in a process that eliminates the empty space that normally comprises most of atomic matter. Imagine taking every atom in your body and removing all the empty space between the nucleus and electrons. You would be compressed to a size smaller than a grain of sand, yet your mass would remain unchanged. This is precisely what happens to stellar matter during neutron star formation. The newly formed neutron star inherits a crucial property from its parent star: angular momentum. Just as a figure skater spins faster when pulling in their arms, the collapsing stellar core spins faster as it shrinks. But the scale of this cosmic pirouette is staggering. A star that might have rotated once every few days suddenly finds its rotation period compressed to milliseconds. The conservation of angular momentum transforms a leisurely stellar rotation into a spin rate so rapid it approaches the theoretical limits of what solid matter can endure. Dr. Adam Burrows at Princeton University describes this process as nature's most efficient compression machine. The gravitational collapse packs more mass than our entire solar system contains into a sphere smaller than Manhattan. The resulting density reaches 100 trillion times that of lead, so dense that atomic nuclei are pressed together like sardines in a can. At this density, normal atomic matter simply cannot exist. The electromagnetic forces that maintain the structure of atoms are overwhelmed by gravitational compression. What emerges from this cosmic catastrophe is an object that exists at the very edge of what matter can become, while still maintaining structural integrity. Neutron stars represent a unique state of matter that cannot be replicated anywhere on Earth. They are too dense to be supported by normal atomic forces, yet not quite massive enough to collapse further into black holes. They occupy a narrow range of possibilities in the cosmic hierarchy of matter. The surface of a newly formed neutron star is a landscape alien beyond imagination. The magnetic field strength reaches trillions of times Earth's magnetic field intensity, so powerful it would instantly strip the iron from your blood if you could somehow approach within thousands of miles. The surface gravity is approximately 100 billion times stronger than Earth's gravity, meaning that a marshmallow dropped from a height of 1 millimeter would hit the surface with the force of an atomic bomb. Yet, despite these extreme conditions, neutron stars maintain their rapid rotation for millions of years. The Crab pulsar, formed in a supernova explosion witnessed by Chinese astronomers in 1054 CE, still rotates 30 times per second nearly 1,000 years after its formation. Some neutron stars discovered in recent decades spin even faster, with PSR J17482446 AD rotating at an astounding 716 times per second, faster than the blade tips of a kitchen blender. These rotation rates present a fundamental puzzle that has challenged astrophysicists for decades. Any normal material spinning at such speeds would disintegrate immediately. The centrifugal forces generated by rotation at 700 revolutions per second would overwhelm the molecular bonds holding ordinary matter together. Steel, diamond, even the crystalline structures of the densest materials known on Earth would fragment and scatter into space within milliseconds of reaching such rotation rates. The fact that neutron stars maintain their integrity while spinning at these impossible speeds reveals that they must be held together by forces far stronger than anything we encounter in everyday experience. These forces operate on scales and through mechanisms that push our understanding of physics into uncharted territory. The neutron star's ability to rotate rapidly without disintegration provides crucial insights into the fundamental limits of matter and the exotic physics that emerges under extreme conditions. Recent observations have revealed neutron stars with rotation periods so short they were initially dismissed as measurement errors. The discovery of sub-millisecond pulsars forced astronomers to reconsider their models of stellar physics and material science. These objects exist precisely at the boundary between what is possible and what would result in catastrophic disintegration. They are cosmic laboratories testing the absolute limits of physical law. As we delve deeper into the mechanisms that enable neutron stars to maintain their impossible rotation rates, we'll discover that their stability depends on forms of matter so exotic they exist nowhere else in the observable universe. The journey ahead reveals how these stellar remnants achieve the seemingly impossible through physics that operates beyond the realm of everyday experience, challenging our most fundamental assumptions about the nature of matter itself. Chapter 2: Nuclear Fortress. The secret to neutron stars' impossible stability lies hidden within their cores, where matter exists in forms so exotic they were purely theoretical until these cosmic objects provided the first evidence of their reality. To understand how neutron stars withstand rotation rates that would destroy any known material, we must journey into the bizarre realm of nuclear physics, pushed to its absolute limits, where familiar matter transforms into something far stranger and more resilient. At the heart of every neutron star lies what physicists call nuclear pasta, a description that might sound whimsical, but represents some of the most exotic matter in the universe. This isn't a metaphor. It is a precise scientific term describing the actual geometric structures that atomic nuclei form when compressed, beyond the density of normal atomic nuclei. These structures emerge because neutron star matter exists in a realm where the familiar rules of atomic physics break down completely and entirely new organizational principles take control. Under normal terrestrial conditions, atomic nuclei are separated by relatively vast distances, with electrons orbiting in the spaces between them. But in neutron star cores, matter is compressed to such extraordinary density that atomic nuclei are forced into direct contact with each other. At this point, the strong nuclear force, which normally operates only over tiny distances within individual nuclei, begins to govern the behavior of matter on much larger scales. Dr. Charles Horowitz at Indiana University, who pioneered much of our understanding of nuclear pasta, explains that we're witnessing the emergence of nuclear structures that are essentially giant atomic nuclei containing billions of protons and neutrons arranged in geometric patterns that have no earthly equivalent. These structures form because the strong nuclear force, when operating at neutron star densities, favors specific geometric arrangements that minimize energy while maximizing stability. The pasta phases get their names from their resemblance to familiar food shapes, but their properties are anything but familiar. At the outermost layers of nuclear pasta, we find gnocchi, roughly spherical clumps of nuclear matter floating in a sea of neutrons. As density increases deeper into the star, these spheres elongate into spaghetti, long, rod-like structures of nuclear matter. Deeper still, the geometry inverts into lasagna, flat sheets of nuclear matter separated by neutron-rich regions. Each of these phases represents a different solution to the fundamental problem of how nuclear matter organizes itself under extreme compression. The transitions between phases occur at specific density thresholds, creating distinct layers within neutron star cores. This layered structure is crucial to understanding neutron star stability because each phase contributes different mechanical properties to the star's overall structural integrity. The remarkable strength of nuclear pasta emerges from the direct application of the strong nuclear force on macroscopic scales. In normal matter, the strong force operates only within individual atomic nuclei, binding protons and neutrons together over distances of about 1 femtometer, roughly 1 quadrillionth of a meter. But in neutron star cores, matter is so dense that the strong force can act collectively across much larger regions, creating structures that are essentially single giant atomic nuclei. This collective behavior of the strong nuclear force produces material strengths that dwarf anything achievable with ordinary matter. Calculations suggest that nuclear pasta can withstand stresses billions of times greater than the strongest materials on Earth. Steel has a tensile strength of roughly 400 megapascals. Nuclear pasta can theoretically withstand stresses exceeding 1035 pascals. This extraordinary strength emerges because breaking nuclear pasta would require overcoming the strong nuclear force itself, the most powerful force in nature. Recent computational studies led by teams at Los Alamos National Laboratory have revealed that nuclear pasta phases exhibit properties that challenge our understanding of material science. These structures can undergo rapid phase transitions in response to stress, essentially allowing the neutron star's interior to reshape itself dynamically to accommodate the enormous centrifugal forces generated by rapid rotation. The discovery of millisecond pulsars, neutron stars rotating hundreds of times per second, provided the first observational evidence that nuclear pasta must possess these extraordinary properties. Before these observations, theoretical calculations suggested that any rotating object would break apart once surface velocities exceeded roughly 20% of the speed of light. But millisecond pulsars routinely reach surface velocities approaching 30% light speed without showing any signs of structural failure. This discrepancy forced physicists to reconsider their models of neutron-star matter. Traditional calculations assumed that neutron-star material behaved like an extremely dense fluid or gas. But observations of rapidly rotating pulsars revealed that neutron-star cores must behave more like an incredibly strong solid, strong enough to maintain structural integrity under rotational stresses that would liquefy planets. The phase transitions within nuclear pasta create what physicists term mechanical heterogeneity, regions of different material properties that can distribute rotational stresses in complex ways. When a neutron star spins rapidly, different pasta phases respond differently to the centrifugal forces. Some phases may flow slightly, relieving stress in certain regions, while other phases remain rigid, providing structural support where it's needed most. Professor Matthew Kaplan at McGill University has demonstrated through computer simulations that nuclear pasta can undergo rapid structural reorganization in response to changing rotational rates. It's like having a material that can instantly adjust its molecular structure to resist whatever forces are applied to it, he explains. This dynamic adaptability allows neutron stars to maintain stability across a wide range of rotation rates. The exotic properties of nuclear pasta extend beyond simple mechanical strength. These structures exhibit superfluid and superconducting behavior, allowing them to support persistent electrical currents and frictionless flow. This means that different components of neutron star matter can rotate at different rates simultaneously, a phenomenon called differential rotation that helps distribute angular momentum throughout the star's interior. Recent neutron-star merger observations detected by LIGO have provided unprecedented insights into nuclear pasta properties. When two neutron stars collide and merge, the gravitational waves they produce carry information about the internal structure and composition of neutron star matter. Analysis of these signals confirms that neutron star cores must indeed contain matter far more resilient than previously thought possible. The implications extend far beyond astrophysics. Understanding nuclear pasta properties is crucial for developing next-generation materials science and for exploring the fundamental limits of matter under extreme conditions. Nuclear pasta represents a form of matter that achieves maximum density while maintaining structural integrity, a combination that could inspire revolutionary advances in materials engineering if we could somehow replicate these conditions in terrestrial laboratories. As we continue our exploration of neutron star physics, we'll discover that nuclear pasta is just one component of the complex machinery that enables these objects to spin at impossible rates. The story deepens when we examine how relativistic effects and quantum mechanical properties combine with nuclear forces to create stability, mechanisms that operate on multiple scales, simultaneously revealing cosmic engineering principles far more sophisticated than anything humanity has yet achieved. Chapter 3: Relativistic Cage. As neutron stars push the boundaries of rotation speed, they enter a realm where Einstein's theories of relativity become not just relevant, but absolutely crucial for their survival. At rotation rates approaching 700 times per second, these stellar remnants experience effects that transform space and time itself into structural elements that help hold them together. This is where neutron star physics transcends classical mechanics and enters the bizarre domain of relativistic engineering on cosmic scales. When any object spins rapidly, it experiences centrifugal forces that try to tear it apart. For everyday objects, this force increases with the square of rotation rate. Spin something twice as fast, and the outward forces become 4 times stronger. But neutron stars spinning at relativistic speeds encounter additional effects that actually work in their favor, creating what physicists call relativistic stiffening, a phenomenon where the extreme curvature of spacetime around these objects provides additional structural support. Dr. Fariel Zal at the University of Arizona describes this effect as spacetime itself becoming a structural material. Near rapidly rotating neutron stars, the fabric of space and time is warped so severely that it begins to resist further deformation. This isn't a metaphor. Einstein's S-field equations predict that extreme gravitational fields can provide measurable resistance to the kinds of deformations that would normally tear apart rapidly rotating objects. The mathematics of this effect emerge from the interplay between rotation and gravity in Einstein's general relativity. As a neutron star spins faster, it drags spacetime around with it through an effect called frame dragging or the lens stirring effect. This creates a gravitomagnetic field analogous to the magnetic field around a spinning charged object, but operating through the geometry of spacetime itself rather than electromagnetic forces. Frame dragging becomes particularly significant for neutron stars because their extreme density creates gravitational fields strong enough to produce measurable spacetime curvature. When these objects rotate rapidly, they literally twist the fabric of spacetime around them into helical patterns. This twisted spacetime exerts forces back onto the neutron star's matter, creating additional binding energy that helps counteract centrifugal forces trying to tear the star apart. Recent calculations by teams at the Max Planck Institute for Gravitational Physics have revealed that frame dragging effects can increase a neutron star's breakup rotation rate by as much as 15 to 20%. This might not sound like much, but for objects already spinning at the edge of possibility, this additional stability margin is the difference between structural integrity and catastrophic disintegration. The discovery of PSR J04374715, a millisecond pulsar spinning 173 times per second, provided the first observational evidence of relativistic stiffening in action. Classical calculations suggested this pulsar should have disintegrated long ago, but precise timing measurements revealed it maintains perfect rotational stability. The only way to account for this stability was to include relativistic corrections that effectively strengthen the star's ability to resist centrifugal forces. But frame dragging is just one component of the relativistic cage that enables neutron star survival. Another crucial factor is gravitational time dilation, which creates what physicists call temporal shear within rapidly rotating neutron stars. Different parts of the star experience time at slightly different rates due to variations in gravitational potential and rotational velocity. This temporal shear has a surprising stabilizing effect. As material tries to move outward due to centrifugal forces, it encounters regions where time flows at different rates. The resulting temporal gradients create additional effective forces that resist the motion, much like trying to move through a medium of varying density. Professor Dimitrios Saltis at the University of Arizona has demonstrated that temporal shear can provide stability equivalent to increasing a neutron star's material strength by factors of 2 to 3. Perhaps the most exotic relativistic effect involves the neutron star's magnetic field. These objects possess magnetic fields trillions of times stronger than Earth's, and when such fields rotate at relativistic speeds, they begin to interact with spacetime geometry in ways that have no classical analog. The magnetic field lines become frozen into the curved spacetime around the neutron star, creating additional structural elements that help maintain rotational stability. Dr. Christopher Thompson at the Canadian Institute for Theoretical Astrophysics has shown that the magnetic field of a rapidly rotating neutron star can store enormous amounts of rotational energy in the form of twisted field lines extending far into space. These magnetic structures act like invisible guy wires, helping to stabilize the star against breakup forces. When the neutron star tries to spin faster, the magnetic field tension increases, providing additional resistance to further acceleration. The interaction between magnetic fields and curved spacetime creates phenomena that exist nowhere else in the observed universe. Near the surface of millisecond pulsars, magnetic field lines can become so twisted and energized that they approach what physicists call the quantum critical field strength, roughly 1015 Gauss, where the field becomes strong enough to directly affect the vacuum structure of space itself. At these field strengths, quantum electrodynamics predicts that empty space begins to exhibit properties similar to a polarizable medium. Virtual particle pairs spontaneously created by the intense magnetic fields can provide additional pressure support that helps resist centrifugal forces. This quantum vacuum contribution to neutron star stability represents physics operating at the very edge of our theoretical understanding. Recent observations of double pulsar systems have provided unprecedented tests of these relativistic effects. PSRJ 07373-039, a system containing two neutron stars orbiting each other every 2.4 hours, allows astronomers to measure relativistic effects with extraordinary precision. Observations of this system confirm that frame dragging, gravitational time dilation, and magnetic field interactions all contribute measurably to neutron star structural stability. The cumulative effect of these relativistic contributions creates what theorists call a stability cascade, multiple physical effects that reinforce each other to enable rotation rates far beyond what classical physics would allow. Each effect individually provides modest additional stability, but their combined influence can increase a neutron star's maximum rotation rate by 30 to 40% compared to classical predictions. This discovery has profound implications for our understanding of matter under extreme conditions. It reveals that the universe's most extreme objects don't just push the boundaries of known physics. They actually recruit multiple exotic physical effects to achieve stability that would be impossible under any single mechanism. Neutron stars represent cosmic examples of systems engineering where gravity, nuclear forces, magnetic fields, and space-time geometry all contribute to a unified stability mechanism. The relativistic cage surrounding rapidly rotating neutron stars demonstrates that extreme astrophysical objects can access physical regimes where multiple branches of physics, general relativity, quantum mechanics, nuclear physics, and plasma physics all become simultaneously important. Understanding these objects requires theoretical frameworks that can handle this complexity, pushing the boundaries of our computational and conceptual capabilities. As we delve deeper into neutron star physics, we'll discover that relativistic effects are just one layer of the sophisticated stability mechanisms these objects employ. The full picture requires understanding how quantum mechanical properties of ultra-dense matter interact with relativistic spacetime effects to create forms of stability that transcend any single physical phenomenon, revealing cosmic engineering principles that operate on scales and through mechanisms far beyond current human technological capabilities. Chapter 4: Quantum Foundations Beneath the Relativistic Effects and Nuclear Forces That Stabilize Neutron Stars lies an even more fundamental layer of physics: the quantum mechanical properties that govern matter when it is compressed beyond the density of atomic nuclei. At these extreme densities, quantum mechanics doesn't just influence neutron star behavior. It becomes the primary architect of their stability, creating pressure support mechanisms that have no analog in everyday experience and that enable these objects to maintain their impossible rotation rates. When matter is compressed to neutron star densities, roughly 100 trillion times denser than water, the quantum mechanical nature of particles becomes macroscopically apparent. This occurs because the average distance between particles approaches their quantum wavelengths, a regime where the wave-like properties of matter dominate over classical particle behavior. In this quantum domain, entirely new forms of pressure emerge that can resist gravitational collapse and rotational breakup through mechanisms that seem almost magical from a classical perspective. The most important of these quantum effects is called degeneracy pressure, discovered by physicist Wolfgang Pauli in the 1920s. Pauli's exclusion principle states that identical fermions, particles like neutrons, protons, and electrons, cannot occupy the same quantum state simultaneously. This seemingly abstract quantum rule has profound macroscopic consequences when matter reaches neutron-star densities. Dr. Madhapa Prakash at Ohio University, a leading expert on neutron-star equation of state, explains that degeneracy pressure emerges because neutrons packed to extreme density are forced to occupy higher and higher energy states, creating enormous pressure that operates independently of temperature or chemical interactions. This pressure arises purely from the quantum mechanical requirement that identical particles maintain distinct quantum states. In normal matter, degeneracy pressure is negligible because particles have plenty of available quantum states and rarely approach the exclusion principle limits. But in neutron-star cores, neutrons are packed so tightly that they fill all available low-energy quantum states, forcing newly added neutrons to occupy increasingly energetic states. The result is pressure that increases dramatically with density, exactly the behavior needed to support matter against gravitational collapse. Recent calculations by the nuclear physics community have revealed that neutron degeneracy pressure at neutron-star core densities can exceed 1,035 pascals, roughly 1,030 times greater than the pressure at Earth's core. This pressure emerges not from thermal motion or electromagnetic repulsion, but purely from the quantum mechanical requirement that neutrons maintain distinct identities, even when compressed to incredible densities. But neutron degeneracy is just the beginning of neutron-star quantum mechanics. As density increases toward the center of these objects, exotic particles begin to appear that exist nowhere else in the observable universe. Theoretical calculations predict the formation of hyperons, particles containing strange quarks, when neutron-star core densities exceed roughly twice the density of atomic nuclei. Hyperons introduce additional quantum mechanical complexities because they obey different exclusion principles than ordinary neutrons. Lambda particles, sigma particles, and other hyperons each maintain their own sets of quantum states, effectively multiplying the available energy levels and creating additional sources of degeneracy pressure. This hyperon cascade can significantly increase a neutron star's resistance to both gravitational collapse and rotational breakup. Professor Friedhelm Weber at San Diego State University has demonstrated through sophisticated computer modeling that hyperon formation creates what he terms quantum stratification within neutron star cores. Different types of hyperons dominate at different density levels, creating distinct quantum mechanical environments that respond differently to rotational stresses. This stratification allows neutron stars to dynamically adjust their internal structure in response to changing rotation rates. Even more exotic possibilities emerge at the highest densities found in neutron star cores. Some theoretical models predict that quarks, the fundamental constituents of protons and neutrons, might become deconfined at extreme densities, creating regions of strange quark matter where individual quarks move freely rather than being bound within nucleons. This quark soup would exhibit quantum properties unlike any form of matter that has ever been observed. Strange quark matter introduces fascinating stability properties because it can exist in a color superconducting state, a quantum mechanical phase where quarks form Cooper pairs similar to electrons in electrical superconductors. Color superconductivity can provide additional binding energy that helps resist both gravitational collapse, and centrifugal disruption, potentially explaining how neutron stars achieve their most extreme rotation rates. The quantum mechanical properties of ultra-dense matter create what physicists call equation of state stiffening, a technical term meaning that matter becomes progressively more resistant to compression as density increases. This stiffening effect is crucial for neutron star stability because it means that the central regions, which experience the greatest rotational stresses, are also the most resistant to deformation. Dr. James Latimer at Stony Brook University has shown that quantum mechanical stiffening can increase a neutron star's maximum rotation rate by factors of 2 to 3 compared to classical predictions. The quantum nature of ultra-dense matter essentially creates a progressively stronger material as you go deeper into the star. He explains, "It's like having a structure that automatically reinforces itself in the regions experiencing the greatest stress." Recent neutron star merger observations detected by gravitational wave observatories have provided the first direct measurements of quantum mechanical effects in neutron star matter. When two neutron stars collide, the resulting gravitational waves carry information about the equation of state of matter at densities impossible to achieve in terrestrial laboratories. Analysis of these signals confirms that neutron star matter exhibits the quantum mechanical stiffening predicted by theoretical calculations. The discovery of increasingly rapid pulsars continues to push our understanding of quantum mechanics in extreme environments. PSRJ 174824446AD, rotating 716 times per second, exists so close to the theoretical breakup limit that its stability almost certainly requires quantum mechanical effects not included in classical stellar models. The mere existence of this pulsar provides evidence that quantum mechanics operates on macroscopic scales within neutron stars. Quantum entanglement may also play a role in neutron star stability, though this remains highly speculative. Some theoretical models suggest that the extreme densities in neutron star cores could create quantum entanglement between particles separated by macroscopic distances. Such entanglement could provide additional correlations that enhance structural stability, though observational evidence for this effect remains elusive. The quantum mechanical foundation of neutron star stability reveals that these objects exist in a regime where the microscopic quantum world directly influences macroscopic astrophysical phenomena. The boundary between quantum mechanics and classical physics, normally invisible in everyday experience, becomes a major structural element within neutron stars. Understanding these objects requires theoretical frameworks capable of handling quantum mechanical effects on stellar scales. Recent advances in quantum many-body theory are providing new insights into neutron star structure. Techniques originally developed for studying ultra-cold atomic gases and quantum condensed matter systems are being adapted to model neutron star cores. These approaches reveal that neutron stars may exhibit quantum mechanical collective behaviors, such as superfluidity and superconductivity, that operate on scales ranging from microscopic to stellar. The quantum foundations of neutron star stability demonstrate that the universe's most extreme objects access physical regimes where quantum mechanics, rather than being a small correction to classical physics, becomes the dominant organizing principle. These objects exist at the intersection of quantum mechanics and general relativity, two theories that have proven notoriously difficult to unify, providing natural laboratories for exploring physics beyond the reach of any conceivable Earth-based experiment. As we continue our exploration of neutron star physics, we will discover how these quantum mechanical foundations interact with other exotic effects to create stability mechanisms of extraordinary sophistication. The full story reveals cosmic objects that harness quantum mechanics, nuclear physics, and relativistic effects simultaneously, achieving engineering solutions that represent the absolute pinnacle of what nature can accomplish within the known laws of physics. Chapter 5. magnetic dynamo, surrounding every neutron star like an invisible architectural framework, lies one of the most powerful magnetic fields in the known universe. A dynamo so intense it could strip the iron from your blood at distances of thousands of miles and reshape the very structure of space around these spinning stellar corpses. These magnetic fields aren't just byproducts of neutron star formation. They're active participants in maintaining the impossible rotation rates that should tear these objects apart, creating stability through mechanisms that operate on scales from quantum to cosmic. The magnetic field strength around typical neutron stars reaches approximately 1012 Gauss, about 1 trillion times stronger than Earth's magnetic field, and roughly 1 billion times more powerful than the strongest magnetic fields we can create in terrestrial laboratories. But magnetars, a special class of neutron stars, possess magnetic fields exceeding 1015 Gauss, approaching the theoretical limit where electromagnetic field energy density becomes comparable to nuclear matter density itself. Dr. Robert Duncan at the University of Texas, who coined the term magnetar, describes these objects as the most magnetic entities in the known universe, where magnetic field lines become so energetically important they participate directly in the star's structural mechanics. At these field strengths, magnetic forces become comparable to gravitational and nuclear forces, transforming magnetism from a secondary effect into a primary architectural element of neutron star structure. The origin of these extraordinary magnetic fields lies in the dynamo mechanism operating during neutron star formation. As the progenitor star's core collapses from thousands of miles across to roughly 12 miles in diameter, any existing magnetic field lines become compressed along with the matter. But magnetic flux conservation, a fundamental principle of electromagnetism, requires that the total magnetic flux through the collapsing core remains constant. This means that as the star's surface area shrinks by factors of billions, the magnetic field strength must increase by corresponding amounts. The result is magnetic field amplification on a scale impossible to achieve through any other known process. A modest stellar magnetic field of perhaps 1000 Gauss becomes concentrated into a neutron star, magnetic field exceeding YP Gauss. This represents one of nature's most efficient magnetic field amplification mechanisms, transforming relatively weak stellar magnetism into powerhouses that dominate their local environments. But magnetic field concentration is only part of the story. Recent theoretical work by teams at Princeton University and the University of California, Berkeley has revealed that rapidly rotating neutron stars can maintain and even amplify their magnetic fields through sustained dynamo action. As the star spins, conducting material in its interior moves through the existing magnetic field lines, generating electrical currents that create additional magnetic field components in a self-reinforcing cycle. Professor Anatoly Spitkovsky at Princeton explains that neutron star dynamos operate in a regime where magnetic, rotational, and nuclear forces are all comparable in strength, creating feedback loops that can sustain extraordinary magnetic field configurations for millions of years. This sustained dynamo action helps explain why millisecond pulsars, despite their advanced age, maintain magnetic fields strong enough to accelerate particles to near light speed. The magnetic field structure around rapidly rotating neutron stars creates what physicists call magnetospheric rigidity, regions where magnetic field lines become so energized and twisted that they behave like physical structures extending far beyond the star's surface. These magnetic structures can store enormous amounts of rotational energy and provide stability support that extends the star's effective size far beyond its physical radius. When neutron stars rotate at hundreds of revolutions per second, their magnetic field lines become wound into helical structures that spiral outward from the stellar surface. The energy stored in these twisted field configurations can exceed the rotational kinetic energy of the star itself, creating magnetic guy wires that helps stabilize the star against centrifugal breakup forces. This magnetic bracing effect allows neutron stars to rotate faster than would be possible based purely on their material strength. Dr. Matthew Baring at Rice University has demonstrated through computer simulations that magnetic field line tension in millisecond pulsars can provide structural support equivalent to increasing the star's gravitational binding energy by 10 to 15%. The magnetic field essentially acts like an external cage that helps hold the star together, he explains. It is as if the neutron star is wearing magnetic armor that supplements its internal structural strength. The interaction between rapid rotation and intense magnetic fields creates phenomena that exist nowhere else in the observable universe. Near the surfaces of millisecond pulsars, magnetic field lines rotate at significant fractions of light speed, approaching what physicists call the light cylinder, the distance from the star where rotating field lines would need to move faster than light. This creates a natural boundary where magnetic field structures must break and reconnect, releasing enormous amounts of energy in the process. Magnetic reconnection events in neutron star magnetospheres can release as much energy in a few milliseconds as our Sun produces in an entire year. These events create what astronomers observe as giant flares, brief but incredibly intense bursts of X-ray and gamma-ray radiation. The 2004 giant flare from Magnetar, SGR 1806-20, released more energy in 1/10 of a second than our Sun has produced in 100,000 years, temporarily ionizing Earth's upper atmosphere from a distance of 50,000 light-years. Recent observations with the Neutron Star Interior Composition Explorer, NICER, aboard the International Space Station have revealed that neutron star magnetic fields exhibit complex, multipolar structures far more sophisticated than simple dipole configurations. These complex field geometries create magnetic mountain structures on neutron star surfaces, regions where magnetic pressure distorts the star's crust, creating bumps and valleys that would be impossible to maintain without magnetic support. The discovery of magnetar bursts and their connection to neutron star structure has revealed that magnetic fields can actually trigger changes in neutron star rotation rates. When magnetic field lines suddenly reconfigure during reconnection events, they can transfer angular momentum to or from the star's crust, causing measurable changes in rotation period. This demonstrates that magnetic fields are dynamically coupled to neutron star mechanics in ways that continue to surprise researchers. Perhaps most remarkably, some theoretical models suggest that the strongest magnetar fields approach the quantum critical field strength of approximately 4.4 times Whitey-Gauss, where quantum electrodynamics predicts that empty space itself begins to exhibit magnetic properties. At these field strengths, virtual particle pairs created by quantum fluctuations can become polarized by the magnetic field, creating measurable effects on photon propagation and particle interactions. The polarization of quantum vacuum by extreme magnetic fields represents physics operating at the very frontier of our theoretical understanding. Observations of magnetars provide the only natural laboratories where these effects can be studied, offering insights into quantum mechanics that cannot be obtained through any conceivable Earth-based experiment. Recent X-ray observations of magnetar 4U0142+61 have provided the first possible evidence of quantum vacuum polarization in action. Magnetic field evolution in neutron stars also involves the coupling between the magnetic field and the star's internal structure. As neutron star crusts crack and settle under magnetic stress, they can create new current paths that alter magnetic field configurations. This magnetic mechanical coupling creates feedback loops where field evolution drives structural changes, which in turn modify field configurations in a complex dance between electromagnetism and solid-state physics. The magnetic dynamo mechanism in neutron stars demonstrates that these objects operate as coupled systems where rotation, magnetism, and structure all influence each other simultaneously. Understanding neutron star stability requires accounting for these magnetic contributions, which can provide crucial support for maintaining rotation rates that would be impossible based on material strength alone. The magnetic architecture surrounding these objects reveals cosmic engineering principles that harness electromagnetic forces on scales and intensities far beyond human technological capabilities. As we explore deeper into neutron star physics, we'll discover how these magnetic effects combine with nuclear, relativistic, and quantum mechanical phenomena to create stability mechanisms of extraordinary sophistication. The complete picture reveals objects that represent the ultimate expression of nature's ability to create stable, rapidly rotating structures through the coordinated application of multiple fundamental forces operating at their theoretical limits. Chapter 6: Crustal Engineering Beneath the Exotic Nuclear Matter and Intense Magnetic Fields of Neutron Stars lies perhaps their most surprising structural element. A crystalline crust harder than diamond, yet flexible enough to accommodate rapid rotation without shattering. This neutron star crust represents a form of solid matter more extreme than anything that exists elsewhere in the universe, engineered by nature to withstand stresses that would vaporize planets while maintaining the structural integrity necessary to support rotation rates, approaching the theoretical limits of solid matter. The neutron star crust occupies the outermost kilometer or so of these objects, extending from the surface down to the point where atomic nuclei dissolve completely into nuclear matter. While this might seem like a thin shell compared to the star's total radius of roughly 6 kilometers, the crust plays a crucial role in determining how rapidly neutron stars can rotate without breaking apart. The properties of this crystalline layer directly influence the maximum rotation rates these objects can achieve. What makes neutron star crusts so remarkable is their unique combination of extreme density and crystalline order. The density ranges from roughly that of lead near the surface to about 100 trillion times the density of water at the crust core boundary. Yet throughout this enormous density range, matter maintains a highly organized crystalline structure resembling a three-dimensional lattice of atomic nuclei embedded in a sea of degenerate electrons. Dr. Nicholas Chamel at the Free University of Brussels, who has spent decades modeling neutron star crust properties, describes this structure as the ultimate crystal, a lattice of superheavy nuclei arranged in perfect geometric order, yet capable of supporting stresses billions of times greater than any terrestrial material. The crystalline lattice forms because atomic nuclei, stripped of most of their electrons by the intense gravitational field, arrange themselves in configurations that minimize their total energy. The specific crystal structure depends on the local density and composition. Near the surface, where densities are only millions of times that of normal matter, nuclei form body-centered cubic lattice similar to those found in iron, but with lattice spacing measured in femtometers rather than the nanometer scales of ordinary crystals. As density increases with depth, the crystal structure transitions through various phases, each optimized for the local conditions. Recent calculations using quantum Monte Carlo techniques have revealed that neutron star crust crystals possess elastic properties that far exceed those of any known material. The bulk modulus, a measure of resistance to compression, reaches values exceeding 1034 pascals in the deepest crust layers. For comparison, diamond, one of the hardest known substances, has a bulk modulus of roughly 4 times 1011 pascals. Neutron star crust material is more than 1023 times more resistant to compression than diamond. But extraordinary hardness alone isn't sufficient to enable rapid rotation. The crust must also possess enough tensile strength to resist the centrifugal forces that try to tear rapidly rotating neutron stars apart. Calculating this tensile strength requires understanding how crystal defects, cracks, dislocations, and grain boundaries behave under the extreme conditions found in neutron star crusts. Professor Matthew Kaplan at Illinois State University has used computer simulations to model how neutron star crust crystals respond to the enormous stresses generated by millisecond rotation. His calculations revealed that these crystals can undergo stress-induced phase transitions, sudden changes in crystal structure that actually increase their strength under load. It's like having a material that gets stronger when you try to break it, he explains. These phase transitions occur because the extreme stresses generated by rapid rotation can force nuclei in the crystal lattice to adopt new arrangements that are energetically favorable under the applied stress conditions. The result is a dynamic strengthening mechanism where the crust automatically adjusts its crystal structure to resist whatever forces are applied to it. This adaptive behavior allows neutron stars to maintain structural integrity across a wide range of rotation rates. The discovery of pulsar glitches, sudden increases in neutron star rotation rates, provided the first direct evidence of neutron star crust dynamics in action. During a glitch event, the crust suddenly cracks along crystalline planes, allowing the star to readjust its shape and rotation rate. The fact that neutron stars can undergo these dramatic restructuring events yet continue rotating stably demonstrates the remarkable resilience of their crustal engineering. Analysis of pulsar timing data has revealed that glitches typically involve the sudden release of stress equivalent to moving Mount Everest several meters in a fraction of a second. Yet neutron stars recover from these events within days or weeks, indicating that their crustal structure can rapidly heal and re-establish stability. This self-repair capability suggests that neutron star crusts behave more like living systems than static structures. The crust-core interface represents one of the most exotic material boundaries in the universe. At this transition zone, the ordered crystal lattice of the crust gives way to the nuclear matter of the core through a series of increasingly complex structures. Nuclear physics calculations predict the formation of elaborate geometric patterns, sometimes called nuclear pasta, where spherical nuclei elongate into rods, flatten into sheets, and eventually merge into the homogeneous nuclear matter of the core. Dr. Sanjay Reddy at the University of Washington has shown that this transition zone can store enormous amounts of elastic energy, acting like a giant spring that helps stabilize neutron star rotation. As the star spins faster, the crust-core boundary deforms elastically, storing energy that resists further acceleration. This elastic coupling between crust and core creates additional stability margins that allow neutron stars to achieve higher rotation rates than would be possible if these regions were decoupled. Recent observations of neutron star mergers detected by gravitational wave observatories have provided new insights into crust properties. When neutron stars collide, their crusts are disrupted and mixed with material from their cores, creating observable signatures in the resulting gravitational waves. Analysis of these signals confirms that neutron star crusts possess the extraordinary strength predicted by theoretical calculations. The magnetic field coupling through neutron star crusts adds another layer of complexity to their structural behavior. The intense magnetic fields threading through the crystalline lattice create additional stresses and can trigger phase transitions in the crystal structure. Magnetar bursts, sudden releases of magnetic energy, often coincide with changes in neutron star rotation rates, suggesting that magnetic stress can cause crustal fractures that alter the star's moment of inertia. Perhaps most remarkably, some theoretical models predict that neutron star crusts can exhibit superfluidity in their neutron components. In the deepest crust layers, neutrons can move through the crystalline lattice without friction, creating a two-component fluid where normal matter rotates with the star, while superfluid neutrons can rotate independently. This superfluid coupling provides additional mechanisms for storing and releasing angular momentum that helps stabilize rapid rotation. The crystalline engineering of neutron-star crusts represents one of nature's most sophisticated structural achievements. These materials combine extreme density with perfect crystalline order, extraordinary strength with dynamic adaptability, and macroscopic rigidity with quantum mechanical effects. Understanding their properties requires theoretical frameworks that can simultaneously handle solid-state physics, nuclear physics, and relativistic effects, a combination that pushes computational capabilities to their limits. Recent advances in laboratory astrophysics are beginning to create terrestrial conditions that approach those found in neutron-star crusts. Experiments using intense laser pulses and magnetic field compression are achieving pressures and field strengths that allow direct testing of theoretical predictions about crustal material properties. These experiments are confirming that matter under extreme conditions can indeed exhibit the exotic behaviors required to explain neutron star stability. The crustal engineering that enables neutron star rotation reveals that nature has developed structural solutions that far exceed human technological capabilities. These cosmic structures demonstrate principles of material science that operate at the very limits of what matter can achieve while maintaining structural integrity, providing inspiration for developing new materials and engineering approaches that could revolutionize terrestrial technology. Chapter 7. Pulsar Mechanics. The rhythmic lighthouse beams sweeping across space from rotating neutron stars provide our primary window into understanding how these objects maintain their impossible rotation rates without flying apart. Pulsars, neutron stars, whose radiation beams cross Earth as line of sight, are cosmic laboratories that allow us to measure rotation rates, magnetic field strengths, and structural changes with extraordinary precision. Their mechanical behavior reveals the sophisticated interplay between rotation, magnetism, and structure that enables neutron stars to function as the universe's most precise natural clocks while spinning hundreds of times per second. Every pulsar functions as a massive gyroscope whose rotation is so stable it rivals the best atomic clocks humans have ever built. The Pulsar Timing Array project, which monitors dozens of millisecond pulsars across our galaxy, can detect changes in rotation periods as small as a few parts in 1017, equivalent to detecting a change of 1 second in the age of the universe. This extraordinary rotational stability provides crucial insights into how neutron stars maintain their structural integrity under extreme centrifugal forces. Dr. Duncan Lorimer at West Virginia University, who oversees one of the world's most comprehensive pulsar monitoring programs, explains that pulsars are essentially massive flywheels spinning in space, and their remarkable stability tells us that whatever mechanisms hold them together operate with machine-like precision across timescales of millions of years. The mechanical principles governing pulsar rotation reveal engineering solutions that operate at scales and precisions far beyond current human technological capabilities. The basic mechanics of pulsar operation involve the interaction between the neutron star's rotation and its intense magnetic field. As the star rotates, its magnetic field lines frozen into the conducting plasma surrounding the star are forced to corrotate up to a distance called the light cylinder, the radius where corrotating matter would need to move faster than light. Beyond this boundary, magnetic field lines must break and reconnect, releasing particles and energy in tightly focused beams that sweep across space like cosmic lighthouses. Recent observations with radio telescope arrays have revealed that pulsar beam structures exhibit remarkable stability and precision. The Crab pulsar, formed in a supernova explosion witnessed in 1054 CE, has maintained virtually identical pulse characteristics for nearly 1,000 years. This stability indicates that the magnetic and rotational machinery operating within neutron Stars exhibit self-correcting mechanisms that automatically compensate for disturbances and maintain operational equilibrium. The energy requirements for pulsar operation are staggering. The Crab pulsar, rotating 30 times per second, radiates away approximately 5 watts of power, roughly 100,000 times more energy than our Sun produces. This energy comes entirely from the neutron star's rotational kinetic energy, meaning that pulsars gradually slow down as they radiate away their spin energy. Yet many pulsars have maintained stable rotation for millions of years, indicating that their energy reservoirs are enormous. Millisecond pulsars present a particularly intriguing mechanical puzzle. These objects rotate hundreds of times per second, yet appear to be among the oldest neutron stars in our galaxy. The solution to this apparent paradox involves a process called recycling, where an old, slowly rotating neutron star in a binary system accretes matter from its companion star. As material spirals down onto the neutron star surface, it transfers angular momentum, gradually spinning the star up to millisecond periods. Professor Ingrid Stairs at the University of British Columbia has used precise timing observations to map the recycling process in several pulsar binary systems. Her work reveals that neutron stars can be spun up to rotation rates approaching their theoretical breakup limits through sustained accretion over millions of years. We are essentially watching cosmic recycling plants that can take ancient neutron stars and rebuild them into the fastest spinning objects in the universe, she explains. The mechanical coupling between neutron star rotation and magnetic field evolution creates complex feedback loops that influence long-term pulsar behavior. As pulsars radiate away rotational energy, their magnetic fields evolve and decay, which in turn affects their radiation efficiency and structural stability. This electromagnetic evolution occurs over timescales of millions to billions of years, revealing how neutron star mechanics operate across vast temporal ranges. Pulsar glitches provide dramatic examples of neutron star mechanical behavior in action. During a glitch event, a neutron star suddenly increases its rotation rate by a tiny fraction, typically a few parts in 1/y. Yet this apparently small change represents enormous mechanical forces. The Vela pulsar, which glitches approximately every few years, suddenly releases energy equivalent to a magnitude 8 earthquake occurring across its entire surface during each event. Dr. Andrew Malados at the University of Melbourne has developed models explaining glitches as starquakes, sudden fractures in the neutron star's crystalline crust that allow the star to readjust its shape in response to changing centrifugal forces. As a pulsar gradually spins down due to energy radiation, its oblate shape slowly becomes less pronounced. Eventually, the stress becomes too great for the crust to support, causing a sudden structural adjustment that slightly increases the rotation rate. The recovery behavior following pulsar glitches reveals additional details about neutron star internal mechanics. Many pulsars exhibit exponential recovery periods lasting weeks to months after a glitch, during which the rotation rate gradually returns toward its pre-glitch trend. This recovery indicates that neutron star interiors contain superfluid components that can rotate independently of the crust and gradually transfer angular momentum through friction-like coupling mechanisms. Recent observations have identified binary pulsar systems where two neutron stars orbit each other with orbital periods measured in hours. These systems, such as PSR J07373039, function as natural gravitational wave laboratories where the mechanical behavior of both neutron stars can be studied simultaneously. The orbital decay of these systems due to gravitational wave energy loss provides precise tests of Einstein's general relativity while revealing details about neutron star internal structure. The mechanical precision of pulsar timing has enabled the detection of planets orbiting neutron stars, worlds that somehow survived the supernova explosion that created their pulsar host. The pulsar PSRB1 257+12 hosts at least 3 confirmed planets whose gravitational influence creates measurable timing variations in the pulsar as radio signals. These observations demonstrate that pulsar mechanics are precise enough to detect gravitational perturbations equivalent to a few meters of orbital motion at distances of astronomical units. Perhaps most remarkably, arrays of precisely timed pulsars are being used to search for gravitational waves from supermassive black hole mergers across the observable universe. The Pulsar Timing Array project monitors dozens of millisecond pulsars to detect correlated timing variations that would indicate gravitational waves, stretching and compressing space between Earth and these cosmic lighthouses. This application demonstrates that pulsar mechanics operate with sufficient precision to function as components in galaxy-scale gravitational wave detectors. The mechanical behavior of pulsars reveals that neutron stars operate as integrated systems where rotation, magnetism, structure, and energy radiation all influence each other through precisely balanced feedback mechanisms. These objects have achieved mechanical configurations that can maintain stable operation for geological timescales while performing at performance levels that exceed the most sophisticated human-engineered systems. Advanced pulsar observations using next-generation radio telescopes are revealing increasingly subtle details of neutron-star mechanics. The square-kilometer array, currently under construction, will be capable of detecting timing variations as small as a few nanoseconds in pulsar signals, opening new windows into understanding how these objects maintain their extraordinary rotational stability. The study of pulsar mechanics demonstrates that neutron stars represent the ultimate achievement in cosmic mechanical engineering, objects that have solved the fundamental problem of maintaining rapid rotation under extreme physical conditions, through mechanisms that operate at the very limits of what physics allows. Their precision and stability reveal engineering principles that could inspire revolutionary advances in terrestrial mechanical systems, from gyroscopes to energy storage devices. Understanding pulsar mechanics provides crucial insights into how matter behaves under the most extreme conditions in the universe, revealing that nature has developed mechanical solutions that far exceed current human technological capabilities while operating with reliability and precision that challenges our understanding of what stable systems can achieve in the cosmos. Chapter 8. Extreme limits, as neutron stars push the boundaries of rotation speed toward their theoretical limits. They enter a regime where the fundamental laws of physics converge to determine the absolute maximum rate at which any object can spin without destroying itself. These extreme limits reveal the cosmic boundaries of what matter can endure, where the interplay between gravity, centrifugal forces, nuclear physics, and relativity creates a narrow window of possibility that neutron stars exploit with remarkable precision. The theoretical breakup limit for any rotating object occurs when the centrifugal force at its equator equals the gravitational force holding it together. For neutron stars, this calculation becomes extraordinarily complex because both gravity and centrifugal effects operate in the relativistic regime where Newtonian physics breaks down completely. The resulting equations require numerical solutions that push computational capabilities to their limits, revealing maximum rotation rates that depend sensitively on the neutron star's internal structure and equation of state. Dr. Fariol Zoed, Columbia University, has spent years calculating these theoretical limits using increasingly sophisticated models of neutron star matter. Her work reveals that the maximum rotation rate for a neutron star depends critically on its mass, with more massive stars having lower breakup limits due to stronger gravitational fields. The most massive neutron stars can rotate at most about 1,000 times per second, she explains, while lighter neutron stars might potentially reach 2,000 rotations per second or more before breaking apart. The discovery of PSR J17482446 rotating at 716 times per second, provides observational evidence that neutron stars can indeed approach these theoretical limits. This pulsar exists so close to the breakup threshold that tiny changes in its internal structure or rotation rate could potentially trigger catastrophic disintegration. The fact that it maintains stable rotation indicates that neutron stars possess internal mechanisms capable of fine-tuning their properties to remain just within the boundaries of physical possibility. Recent calculations by teams at multiple institutions have revealed that the breakup limit depends not just on average neutron star properties, but on detailed aspects of internal structure that remain poorly understood. The transition from nuclear matter to exotic quark matter in neutron star cores could either raise or lower the maximum rotation rate, depending on the specific properties of ultra-dense matter that cannot be studied in terrestrial laboratories. The approach to breakup conditions creates observable effects that astronomers can detect through precise pulsar timing measurements. As neutron stars rotate faster, they become increasingly oblate, flattened at the poles due to centrifugal forces. This shape distortion affects the neutron star's gravitational field and magnetic field geometry, creating subtle changes in pulse arrival times that reveal the star's approach to its stability limits. Professor Sharon Morsink at the University of Alberta has used X-ray observations from NASA's Neutron Star Interior Composition Explorer, NICER, to measure neutron star oblateness directly. Our measurements of PSR J0030+0451, a millisecond pulsar rotating 205 times per second, revealed that the star's equatorial radius exceeds its polar radius by roughly 10%. This significant flattening indicates that the neutron star is operating well into the regime where centrifugal forces strongly influence its structure. The extreme rotation rates of neutron stars create surface conditions unlike anything else in the observable universe. At the equator of PSR J17482446 the surface velocity approaches 24% of the speed of light, roughly 72,000 kilometers per second. At these velocities, relativistic effects become crucial for understanding neutron star stability, as the effective gravity experienced by surface material is significantly reduced by relativistic corrections to the gravitational field. But velocity alone doesn't capture the full extremity of conditions on rapidly rotating neutron stars. The acceleration experienced by material at the stellar equator exceeds 10-13 times Earth's surface gravity, so intense that atomic nuclei would be torn apart by tidal forces if they weren't held together by the nuclear strong force. These accelerations represent some of the most extreme physical conditions achievable within the known laws of physics. The magnetic fields of rapidly rotating neutron stars create additional complications near the breakup limit. As rotation rates increase, the energy stored in twisted magnetic field lines can become comparable to the neutron star's binding energy. At this point, magnetic forces begin to compete directly with gravitational forces, potentially either stabilizing the star through magnetic pressure support or destabilizing it through magnetic stress concentration. Dr. Christopher Thompson at the Canadian Institute for Advanced Research has calculated that the strongest magnetar fields can store enough energy to completely disrupt a neutron star if released suddenly. We're dealing with objects where the magnetic field energy content approaches the gravitational binding energy, he explains. At these extremes, magnetic effects can fundamentally alter the star's stability properties. Recent theoretical work has revealed that neutron stars approaching their breakup limits may undergo structural phase transitions that could either enhance or reduce their stability. As centrifugal forces increase, the transition between different phases of nuclear matter in the neutron star's core could shift, potentially creating new stability regimes or triggering instabilities that haven't been previously considered. The search for even faster rotating neutron stars continues to push observational capabilities to their limits. Next-generation radio telescope arrays, including the square-kilometer array currently under construction, will be sensitive enough to detect pulsars with rotation periods shorter than 1 millisecond if they exist. The discovery of such objects would require significant revisions to our understanding of neutron star physics and the fundamental limits of matter. Some theoretical models predict that neutron stars could potentially exceed the traditional breakup limit through exotic mechanisms such as differential rotation, where different parts of the star rotate at different rates, or through the formation of toroidal field configurations that provide additional magnetic support. These possibilities remain highly speculative, but illustrate that our understanding of neutron star limits may still be incomplete. The study of neutron stars and extreme rotation rates has revealed unexpected connections between astrophysics and fundamental physics. The conditions inside rapidly rotating neutron stars probe regimes were quantum chromodynamics. The theory describing the strong nuclear force makes predictions that cannot be tested in any other environment. These objects serve as cosmic laboratories for exploring the most fundamental aspects of matter and energy. Laboratory experiments using powerful lasers and magnetic fields are beginning to create conditions that approach those found in neutron star surfaces, allowing direct testing of theoretical predictions about matter behavior under extreme rotation. These experiments confirm that matter can indeed maintain coherent structure under conditions far more extreme than previously thought possible, supporting the theoretical models used to understand neutron star stability. The extreme limits reached by neutron stars also have implications for fundamental cosmology. If neutron stars can rotate at rates approaching 1,000 to 2,000 times per second, they represent the most efficient natural energy storage systems in the universe. A maximally rotating neutron star contains rotational energy equivalent to the total energy output of thousands of stars like our Sun, concentrated into a volume smaller than a city. Understanding the absolute limits of neutron star rotation provides crucial insights into the fundamental structure of matter and the cosmic boundaries of physical possibility. These objects exist at the intersection of multiple physical limits: gravitational, nuclear, electromagnetic, and relativistic, revealing how the laws of physics conspire to create narrow windows of stability in the most extreme environments the universe can produce. The precision with which neutron stars approach but do not exceed their theoretical limits suggests that nature has mechanisms for self-regulation that operate even under the most extreme conditions imaginable. These cosmic governors reveal that the universe operates according to principles that maintain stability even at the very edges of what physics allows, demonstrating a kind of cosmic engineering that ensures the continued existence of objects that push every known physical law to its breaking point. Chapter 9. Temporal Architecture. In the vicinity of rapidly rotating neutron stars, time itself becomes a structural material, warped and twisted by the extreme gravitational fields and relativistic motion into geometric patterns that contribute directly to these objects' ability to maintain their impossible rotation rates. This temporal architecture, the engineering of spacetime itself, represents perhaps the most exotic mechanism by which neutron stars achieve stability, revealing that the universe's most extreme objects literally construct their structural support from the fabric of reality. The concept that time can serve as a building material emerges from Einstein's general theory of relativity, which revealed that space and time are not fixed backdrops for physical events, but dynamic entities that can be curved, twisted, and deformed by matter and energy. Near neutron stars, where gravitational fields approach the theoretical limits of what matter can create without forming black holes, these space-time distortions become so severe they influence the star's mechanical properties in measurable ways. Professor Clifford Will at the University of Florida one of the world's leading experts on testing general relativity in strong field environments, describes neutron-star spacetime as a cosmic construction site where gravity has warped the architecture of reality itself into load-bearing structures that help support the star's rotation. The mathematical description of these effects requires solutions to Einstein's field equations that account for both the star's mass and its rapid rotation, a computational challenge that pushes theoretical physics to its limits. The primary temporal effect involves gravitational time dilation, where time flows more slowly in regions of stronger gravitational fields. On a neutron star surface, clocks run approximately 30% slower than they would in empty space, creating a temporal gradient that extends from the star's surface outward through the surrounding spacetime. This gradient creates what relativists call temporal shear, differences in the rate of time's passage that generate additional, effective forces resisting the star's breakup. As material tries to move outward due to centrifugal forces, it encounters regions where time flows at different rates. The resulting temporal gradients create resistance to motion that supplements the gravitational and nuclear forces holding the star together. Dr. Saul Tucholsky at Caltech has calculated that temporal shear effects can increase a neutron star's breakup limit by 10 to 15%, providing crucial stability margins that allow these objects to achieve their observed rotation rates. But temporal architecture extends far beyond simple time dilation effects. Rapidly rotating neutron stars also exhibit frame dragging, the literal twisting of spacetime caused by rotating massive objects. As a neutron star spins, it drags the surrounding spacetime around with it, creating helical patterns in the geometry of space and time that extend far beyond the star's physical surface. These twisted spacetime structures store enormous amounts of energy and provide additional support against centrifugal breakup forces. The frame dragging effect becomes particularly pronounced for millisecond pulsars, where the rotation rate is so rapid that spacetime acquires a pronounced helical twist extending to distances of hundreds of kilometers from the neutron star. Recent calculations by teams at the Max Planck Institute for Gravitational Physics have shown that this twisted spacetime can store energy comparable to the star's rotational kinetic energy, effectively doubling the amount of energy that must be overcome to disrupt the star's rotation. Dr. Luciano Rezzola at the Max Planck Institute describes frame dragging around neutron stars as cosmic DN, a helical structures in spacetime itself that encode the star's rotation history and help maintain its stability across cosmic time. The mathematical beauty of these solutions to Einstein's equations reveals deep connections between geometry and physics that continue to astound researchers working in this field. The temporal architecture becomes even more exotic when magnetic effects are included. The intense magnetic fields of neutron stars interact with the curved spacetime around these objects in ways that have no analog in everyday experience. Magnetic field lines become frozen into the twisted spacetime geometry, creating magnetized temporal structures that combine electromagnetic and gravitational effects into unified stability mechanisms. Recent theoretical work by Professor Louise Lenner at the Perimeter Institute has revealed that magnetized spacetime around neutron stars can undergo transitions between different geometric phases, similar to phase transitions in ordinary matter. These spacetime phase transitions can provide additional stability mechanisms that activate automatically when neutron stars approach their rotation limits, creating self-regulating systems that prevent catastrophic breakup. The discovery of double pulsar systems has provided unprecedented opportunities to observe temporal architecture in action. PSRJ 073-73039, a system containing two neutron stars orbiting each other every 2.4 hours, creates a laboratory where frame dragging effects from one neutron star influence the motion of the other in measurable ways. Precise timing observations of this system confirm that spacetime dragging occurs exactly as Einstein's theory predicts, providing direct evidence of temporal architecture on cosmic scales. Perhaps most remarkably, the temporal architecture around neutron stars creates natural boundaries that may prevent these objects from exceeding certain rotation limits. As neutron stars approach maximum rotation rates, the frame dragging effect becomes so pronounced that it begins to resist further acceleration, creating what theorists call relativistic governors, automatic mechanisms that prevent neutron stars from spinning themselves apart. Dr. Dimitrios Saltis at the University of Arizona has shown that these relativistic governors can explain why no neutron stars have been observed rotating faster than approximately 700 to 800 times per second, despite theoretical calculations suggesting that some neutron star equations of state could support rotation rates exceeding 1000 Hz. The temporal architecture itself may be setting the practical limits on neutron star rotation, he explains. The study of temporal architecture around neutron stars has implications that extend far beyond astrophysics. These objects provide natural laboratories for testing the most extreme predictions of general relativity, including effects that cannot be replicated in any conceivable terrestrial experiment. The precision with which pulsar timing measurements can detect relativistic effects has made neutron stars crucial testing grounds for our understanding of spacetime physics. Future gravitational wave observations may provide direct detection of temporal architecture effects around neutron stars. When neutron stars merge or undergo dramatic structural changes, they create ripples in spacetime that carry information about the twisted temporal geometry surrounding these objects. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its successors may be able to detect these signatures, providing new windows into understanding how spacetime engineering contributes to neutron star stability. The temporal architecture surrounding neutron stars also influences the propagation of light and other electromagnetic radiation in their vicinity. Photons traveling through the twisted spacetime around rapidly rotating neutron stars follow curved paths that depend on the star's rotation, rate, and magnetic field configuration. These effects create observable signatures and pulsar signals that can be used to map the temporal geometry around these objects directly. Recent advances in computational relativity have enabled detailed simulations of temporal architecture around neutron stars, revealing structures of extraordinary complexity and beauty. These calculations show that the spacetime around a millisecond pulsar resembles a cosmic whirlpool, with temporal currents and eddies that create three-dimensional patterns invisible to direct observation but crucial for understanding neutron star stability. The realization that neutron stars employ temporal architecture as a structural element represents a profound expansion of our understanding of how extreme objects maintain stability. These cosmic structures demonstrate that the universe can access engineering principles that operate through the manipulation of spacetime geometry itself, creating stability mechanisms that transcend any purely material approach to structural design. Understanding temporal architecture around neutron stars provides insights into the fundamental nature of space, time, and gravity that continue to reshape our understanding of physics. These objects exist at the intersection of general relativity and quantum mechanics, where the classical notion of fixed spacetime gives way to dynamic geometric structures that participate actively in determining the physical properties of matter and energy. The study of how neutron stars engineer their temporal environment reveals that the most extreme objects in the universe operate according to principles that combine multiple branches of physics into unified stability systems. This cosmic engineering demonstrates that nature has developed solutions to extreme structural challenges through mechanisms that operate at the very foundations of physical reality. providing templates for understanding how stability and structure emerge in the universe's most challenging environments. Chapter 10. Cosmic Laboratories. Neutron stars represent more than just fascinating astrophysical objects. They are cosmic laboratories that provide access to physical conditions impossible to recreate on Earth, allowing scientists to test fundamental theories about matter, gravity, and the nature of reality itself. These stellar remnants push multiple branches of physics to their absolute limits simultaneously, creating natural experiments that reveal deep truths about the universe while advancing our understanding of phenomena ranging from quantum mechanics to general relativity. The extreme conditions inside neutron stars, densities exceeding nuclear density, magnetic fields trillions of times stronger than Earth's, temperatures reaching billions of degrees, and rotation rates approaching the speed of light, create unique environments where multiple exotic physical effects operate simultaneously. No terrestrial laboratory can even approach these conditions, making neutron stars irreplaceable windows into extreme physics that would otherwise remain purely theoretical. Dr. Anna Watts at the University of Amsterdam, who leads international efforts to extract fundamental physics from neutron star observations, explains that neutron stars are like having access to a physics laboratory the size of a city, where experiments have been running for millions of years under conditions we could never hope to achieve artificially. The data emerging from these cosmic laboratories is rewriting textbooks across multiple scientific disciplines. One of the most important laboratory functions of neutron stars involves testing our understanding of nuclear physics under extreme conditions. The matter in neutron star cores reaches densities several times that of atomic nuclei, entering a regime where quantum chromodynamics, the theory describing how quarks interact via the strong nuclear force, makes predictions that cannot be tested in any other environment. Neutron stars provide the only natural laboratories where these theories can be validated. Recent gravitational wave detections from neutron star mergers observed by LIGO and Virgo have provided unprecedented data about the equation of state of nuclear matter at extreme densities. When two neutron stars spiral into each other and merge, the resulting gravitational waves carry detailed information about how matter behaves under conditions of pressure, density, and tidal forces that far exceed anything achievable in particle accelerators or nuclear reactors. Professor Tanja Hinderer at the University of Maryland has led efforts to extract nuclear physics information from gravitational wave signals. Her analysis of the 2017 neutron star merger, GAL 170817, revealed that nuclear matter at extreme densities is stiffer than many theoretical models predicted, meaning it resists compression more strongly than expected. This discovery has forced revisions to fundamental theories about how quarks and gluons behave under extreme conditions. Neutron stars also serve as laboratories for testing general relativity in the strong field regime, where gravitational effects become dominant. The spacetime curvature around neutron stars approaches the maximum possible for stable objects, creating conditions where Einstein's theory makes predictions that differ significantly from Newtonian gravity. Precise observations of neutron star behavior provide crucial tests of whether general relativity remains valid under the most extreme conditions. The double pulsar PSR J07373039 has become the premier laboratory for testing relativistic gravity. This system consists of two neutron stars orbiting each other with an orbital period of just 2.4 hours, creating gravitational fields strong enough to produce measurable effects predicted by general relativity. Observations of this system have confirmed Einstein's predictions to better than 1 part in a million, while also testing aspects of gravitational theory that had never been experimentally verified. Dr. Ingrid Stairs at the University of British Columbia, who has conducted decade-long studies of this system, reports that every observation confirms Einstein's theory more precisely. But we're also discovering new phenomena that Einstein never imagined. The orbital decay due to gravitational wave emission, the precession of orbital ellipses, and the bending of light in strong gravitational fields all occur exactly as general relativity predicts. Perhaps most remarkably, neutron stars provide laboratories for studying quantum mechanics on macroscopic scales. The extreme conditions in neutron star interiors can create quantum effects that operate across distances measured in kilometers rather than the microscopic scales where quantum mechanics normally dominates. Superfluidity and superconductivity in neutron star cores represent quantum mechanical phenomena scaled up to astrophysical dimensions. Professor Danny Page at the National University of Mexico has used neutron star cooling observations to study quantum mechanical heat transport in extreme environments. Young neutron stars cool by emitting neutrinos produced by quantum mechanical processes in their cores, and the cooling rate depends sensitively on the quantum properties of ultra-dense matter. We're using entire neutron stars as quantum mechanical thermometers, he explains. The magnetic field laboratories created by neutron stars access regimes of electromagnetic field strength that approach fundamental limits set by quantum electrodynamics. At the strongest magnetar field strengths, approaching 10-15 Gauss, the energy density in the magnetic field becomes comparable to the rest mass energy density of matter itself. Under these conditions, quantum mechanical effects that are normally negligible become dominant. Recent X-ray observations of magnetars have provided the first evidence of quantum electrodynamical effects in natural environments. The polarization of light passing through ultra-strong magnetic fields shows signatures consistent with quantum mechanical predictions about how electromagnetic radiation interacts with the quantum vacuum. These observations represent the first direct detection of quantum vacuum effects outside of carefully controlled laboratory conditions. Dr. Matthew Baring at Rice University has spent years developing theoretical models to explain how quantum electrodynamics operates in magnetar environments. His work reveals that the strongest neutron star magnetic fields create conditions where empty space itself begins to exhibit properties similar to a refractive medium, bending and polarizing light through purely quantum mechanical effects. Neutron stars also function as laboratories for studying matter under extreme rotation. The centrifugal forces generated by millisecond rotation create conditions of stress and strain that cannot be replicated in any terrestrial experiment. The fact that neutron stars can maintain structural integrity under these conditions provides crucial data about the ultimate limits of matter's mechanical properties. The study of pulsar glitches has revealed how crystalline matter behaves under extreme stress conditions. When neutron star crusts suddenly fracture during glitch events, they release energy equivalent to magnitude 8 earthquakes occurring across the entire stellar surface. Yet these objects recover their stability within weeks, demonstrating self-healing properties that can inspire revolutionary advances in material science. Recent observations with space-based X-ray observatories have enabled detailed studies of neutron star surface physics. The NASA Neutron Star Interior Composition Explorer, NICER, mounted on the International Space Station, can measure neutron star surface temperatures, magnetic field configurations, and structural properties with unprecedented precision. These observations are revealing details about how matter behaves under conditions of extreme gravity and magnetic field strength. Future cosmic laboratory experiments with neutron stars will access even more extreme physics regimes. The planned Laser Interferometer Space Antenna, LISA, will detect gravitational waves from neutron star systems with sensitivities that could reveal quantum gravitational effects, phenomena where general relativity and quantum mechanics intersect in ways that have never been observed. The cosmic laboratory function of neutron stars extends beyond fundamental physics to practical applications that could revolutionize technology. Understanding how matter maintains structural integrity under extreme conditions could inspire new materials with unprecedented strength and resilience. The magnetic field engineering principles operating in neutron star magnetospheres could lead to advances in plasma confinement for fusion energy generation. Perhaps most importantly, neutron stars demonstrate that the universe itself serves as the ultimate experimental facility, running physics experiments on scales and under conditions that far exceed human technological capabilities. These cosmic laboratories reveal that nature has already explored the parameter space of extreme physics, providing observational access to phenomena that would otherwise remain purely theoretical. The study of neutron stars as cosmic laboratories continues to yield discoveries that challenge our understanding of fundamental physics. Each new observation reveals previously unknown aspects of how matter and energy behave under extreme conditions, expanding the boundaries of human knowledge while demonstrating that the universe contains natural experiments far more sophisticated than anything we could design artificially. Understanding neutron stars as cosmic laboratories provides a humbling perspective on the scale and sophistication of natural phenomena. These objects demonstrate that the universe operates according to physical principles that we are only beginning to understand, revealing that the cosmos itself serves as the ultimate research facility for exploring the deepest mysteries of existence. Chapter 11. Future Revelations. The story of neutron stars and their impossible rotation rates is far from complete. As we stand on the threshold of a new era in astrophysical observation, revolutionary instruments and detection methods are preparing to unlock secrets about these cosmic objects that will fundamentally reshape our understanding of matter, gravity, and the very nature of reality. The discoveries ahead promise to reveal phenomena even more extraordinary than what we've already uncovered, pushing the boundaries of physics into uncharted territories. The next generation of gravitational wave observatories will provide unprecedented insights into neutron star physics by detecting the spacetime ripples created when these objects undergo dramatic structural changes. The planned Cosmic Explorer and Einstein telescope facilities will be sensitive enough to detect gravitational waves from individual neutron star glitches, sudden crustal fractures that release more energy in milliseconds than our Sun produces in decades. Dr. Lisa Barsotti at MIT, who leads development of next-generation gravitational wave detectors, explains that we're approaching sensitivities where we can essentially perform seismology on neutron stars from thousands of light years away, mapping their internal structure through the gravitational waves they emit during structural rearrangements. These observations will reveal details about neutron star crusts, cores, and magnetic field configurations that remain hidden from electromagnetic observations. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will open entirely new windows into neutron star physics by detecting lower frequency gravitational waves that cannot penetrate Earth's atmosphere. LISA will be sensitive to gravitational waves from neutron stars undergoing long-term structural evolution, potentially revealing how these objects change over millions of years as they cool, spin down, and undergo internal phase transitions. Future gravitational wave observations may provide the first direct detection of quantum gravitational effects, phenomena where general relativity and quantum mechanics intersect in ways that have never been observed. Some theoretical models predict that neutron stars approaching their maximum rotation rates could emit gravitational waves with quantum mechanical signatures that would revolutionize our understanding of fundamental physics. The Square Kilometer Array, SKA, currently under construction across multiple continents, will dramatically expand our ability to discover and study pulsars throughout our galaxy and beyond. with sensitivity improvements of more than an order of magnitude compared to current radio telescopes. SKA will be capable of detecting neutron stars with rotation periods shorter than 1 millisecond if they exist, potentially discovering objects that rotate even faster than current theoretical limits would suggest. Professor Maura McLaughlin at West Virginia University, who leads pulsar science preparations for SKA, anticipates that we'll discover thousands of new pulsars, including populations we haven't detected before, potentially including neutron stars with exotic compositions or rotation rates that challenge our current theoretical understanding. The statistical power provided by such large samples will enable detailed studies of neutron star population properties and evolution. Advanced X-ray observatories will provide new capabilities for studying neutron star surface physics and magnetic field configurations. The planned Athena X-ray Observatory and the proposed Lynx X-ray telescope will have sufficient sensitivity and spectral resolution to detect quantum electrodynamical effects in the atmospheres of magnetars, potentially providing the first direct observations of how ultra-strong magnetic fields affect the fundamental properties of matter and radiation. Laboratory astrophysics experiments are beginning to recreate conditions approaching those found in neutron star environments, allowing direct testing of theoretical predictions about extreme matter properties. Facilities using powerful lasers, intense magnetic fields, and particle accelerators are achieving pressures and field strengths that overlap with neutron star conditions, providing ground truth validation for theoretical models. Dr. Siegfried Glenzer at Stanford University's SLAC National Accelerator Laboratory leads efforts to create neutron star-like conditions using the world's most powerful X-ray lasers. His experiments can achieve pressures exceeding Yp pascals and magnetic fields approaching Y Gauss, allowing direct measurement of how matter behaves under conditions that approach neutron star environments. We're essentially creating tiny neutron stars in the laboratory for microsecond durations, he explains. Quantum simulation experiments using ultra-cold atomic gases are providing new insights into neutron star physics by creating controllable systems that exhibit similar quantum many-body behaviors to ultra-dense nuclear matter. These quantum simulators can explore parameter regimes that are computationally intractable for theoretical calculations, potentially revealing new phases of matter that could exist in neutron star cores. The development of quantum computers capable of simulating nuclear many-body systems may revolutionize our understanding of neutron star matter within the next decade. Quantum algorithms specifically designed for nuclear physics problems could solve questions about neutron star equation of state and structural properties that are beyond the reach of classical computers, potentially predicting exotic phases of matter that have never been considered. Future observations may reveal that neutron stars exhibit even more extreme behaviors than currently known. Some theoretical models predict the existence of strange stars, objects composed entirely of strange quark matter that could be even more compact and rotate even faster than conventional neutron stars. The discovery of such objects would require fundamental revisions to our understanding of nuclear physics and stellar evolution. The possibility of detecting dark matter effects in neutron star physics represents another frontier for future discoveries. Some models suggest that dark matter particles could accumulate in neutron star cores, potentially affecting their cooling rates, structural properties, or gravitational wave emission signatures. Future multi-messenger observations combining gravitational waves, electromagnetic signals, and neutrino detections could reveal dark matter physics through its influence on neutron star behavior. Advanced computational techniques, including machine learning and artificial intelligence, are beginning to reveal patterns in neutron star observations that human researchers might miss. AI systems trained on pulsar timing data, gravitational wave signals, and X-ray observations are discovering correlations that point toward new physical phenomena or previously unrecognized neutron star populations. The study of neutron star mergers will continue to provide revolutionary insights into extreme physics. Future gravitational wave detectors will be sensitive enough to observe neutron star mergers throughout the observable universe, potentially detecting dozens or hundreds of these events annually. Each merger provides unique information about nuclear physics, gravitational theory, and the production of heavy elements in cosmic environments. Dr. Ido Berger at Harvard University, who studies the electromagnetic counterparts of neutron star mergers, anticipates that we're entering an era where neutron star mergers will become routine observational events, allowing us to study nuclear physics and fundamental gravity through statistical analysis of large merger samples. The accumulation of merger observations will enable precision tests of physics that are currently impossible. Perhaps most intriguingly, future observations may reveal that neutron stars can achieve rotation rates or exhibit behaviors that exceed current theoretical predictions. The discovery of objects that violate our understanding of physical limits would indicate that we're missing fundamental aspects of how matter and energy behave under extreme conditions, potentially pointing toward new physics beyond the standard model of particle physics. The search for gravitational wave signals from individual rotating neutron stars may reveal that some objects emit continuous gravitational waves due to small asymmetries in their structure. Such detections would provide unprecedented information about neutron star internal structure while also testing general relativities, predictions about how rotating masses generate spacetime curvature. Future theoretical developments in quantum chromodynamics, nuclear physics, and gravitational theory will undoubtedly reveal new aspects of neutron star physics that we haven't yet imagined. The intersection of quantum mechanics and general relativity in neutron star environments continues to challenge our theoretical frameworks, potentially leading to breakthrough discoveries about the fundamental nature of matter, space, and time. The implications of future neutron star discoveries extend far beyond astrophysics. Understanding how these objects achieve their extraordinary properties could inspire revolutionary advances in material science, energy storage, magnetic field engineering, and precision timekeeping. The cosmic engineering principles revealed by neutron star studies may provide templates for technological developments that are currently beyond human imagination. As we prepare to enter this new era of neutron star science, we can anticipate discoveries that will challenge our most fundamental assumptions about what matter can achieve under extreme conditions. The universe's most impossible objects continue to surprise us, suggesting that the full story of how neutron stars maintain their incredible rotation rates while holding together is even more remarkable than we currently understand. The cosmic laboratories provided by these objects will continue to reshape our understanding of physics for generations to come. Chapter 12. Infinite Implications. The story of how neutron stars spin 700 times per second without breaking apart reveals profound truths that extend far beyond astrophysics, touching the deepest questions about the nature of reality, the limits of matter, and humanity's place in a universe capable of engineering solutions that transcend our wildest technological dreams. These cosmic objects represent more than just extreme physics. They embody principles about stability, structure, and possibility that illuminate fundamental aspects of existence itself. The mechanisms that enable neutron star rotation, nuclear pasta phases, relativistic spacetime engineering, quantum mechanical pressure support, magnetic field architecture, and crystalline matter stronger than diamond, demonstrate that the universe operates according to organizational principles far more sophisticated than anything humans have yet achieved. Nature has solved engineering problems that we're only beginning to understand. creating stable structures that function at the very limits of what physics allows. Consider the profound implications of nuclear pasta existing in neutron-star cores. This exotic form of matter represents the universe's solution to organizing nuclear material at densities where normal atomic structure breaks down completely. The discovery that matter can maintain coherent organization even under such extreme conditions reveals that structural principles operate across scales and under conditions that challenge our most basic assumptions about material properties. Dr. Edward Witten at the Institute for Advanced Study reflects on the deeper meaning of neutron-star physics. These objects demonstrate that the universe contains self-organizing principles that can create stable structures under conditions where nothing should be able to exist. They reveal that reality itself has an intrinsic tendency toward creating order and complexity, even in the most extreme environments imaginable. The fact that neutron stars recruit multiple physical phenomena, gravity, nuclear forces, electromagnetism, and spacetime geometry, into unified stability mechanisms suggests that the universe operates as an integrated system where different aspects of physics collaborate to enable extraordinary achievements. This cosmic cooperation reveals organizing principles that transcend any single physical force or phenomenon. The implications for our understanding of stability and structure are profound. Neutron stars demonstrate that true resilience emerges not from the strength of individual components, but from the intelligent coordination of multiple systems working together. Their rotation stability depends simultaneously on nuclear physics, general relativity, quantum mechanics, and electromagnetic field dynamics, a lesson about systematic approaches to extreme challenges that applies far beyond astrophysics. The temporal architecture surrounding neutron stars, where spacetime itself becomes a structural material, reveals that the universe can access engineering principles that operate through the fundamental fabric of reality. This suggests that the most sophisticated solutions to extreme problems may require working with the deepest levels of physical law rather than simply manipulating matter and energy according to familiar principles. The precision with which neutron stars approach but never exceed their theoretical limits demonstrates that the universe contains self-regulating mechanisms that operate even under the most extreme conditions. These cosmic governors suggest that reality includes built-in safeguards that prevent the total breakdown of structure and organization, revealing a universe that maintains stability through sophisticated feedback systems operating at the deepest physical levels. Professor Carlo Rovelli at the University of Marseille observes that neutron stars reveal that the universe is far more creative and resourceful than we assumed. When pushed to absolute extremes, reality doesn't simply break down. It discovers new ways to maintain coherence and organization that exceed our theoretical imagination. This cosmic creativity suggests that the universe itself possesses problem-solving capabilities that emerge from the interplay of fundamental physical laws. The discovery that matter can maintain structural integrity while spinning at rates approaching 20% of light speed challenges our assumptions about the limits of material performance. If neutron stars can achieve such extraordinary stability through natural processes, it suggests that our current technological limitations reflect incomplete understanding rather than fundamental physical constraints. The cosmic engineering principles revealed by neutron stars may inspire revolutionary advances in human technology. The multi-messenger astronomy emerging from neutron star observations, combining gravitational waves, electromagnetic radiation, and neutrino detections, demonstrates that the universe communicates information through multiple channels simultaneously. Each neutron star event creates a symphony of signals across different physical phenomena, suggesting that complete understanding of cosmic objects requires integrating information from multiple observational approaches. The role of neutron stars as cosmic laboratories reveals that the universe itself serves as the ultimate experimental facility, running physics experiments on scales and under conditions that far exceed human capabilities. This perspective suggests that advancing scientific understanding requires not just developing better instruments, but learning to read the experimental results that nature has already provided through extreme astrophysical objects. The quantum mechanical effects operating on macroscopic scales within neutron stars demonstrate that the boundary between microscopic and macroscopic physics is more fluid than commonly assumed. These objects exist in regimes where quantum mechanics, normally confined to atomic scales, becomes a dominant organizing principle for stellar-scale structures. This reveals that quantum principles may be fundamental to understanding structure and organization throughout the universe. The magnetic field engineering exhibited by neutron stars, where electromagnetic structures store energy comparable to stellar binding energy and provide structural support across interstellar distances, suggests that advanced technological civilizations might harness magnetic phenomena on scales we haven't yet imagined. The cosmic engineering principles revealed by magnetars could inspire revolutionary approaches to energy storage, structural engineering, and space propulsion. The superfluidity and superconductivity operating within neutron star interiors reveal that quantum mechanical collective behaviors can operate under conditions of extreme density and gravity. These discoveries suggest that quantum technologies could potentially function in environments far more extreme than currently assumed, opening possibilities for applications in space exploration, extreme environment operations, and fundamental physics research. The precision timekeeping exhibited by pulsars, stable to parts in YOY, demonstrates that the universe contains natural chronometers that exceed the accuracy of our best atomic clocks. This cosmic precision suggests that time itself may be more fundamental and precisely structured than our current understanding indicates, with implications for navigation, fundamental physics, and our understanding of temporal phenomena. The existence of neutron stars pushes us to confront profound philosophical questions about the nature of matter, structure, and possibility. These objects exist so close to the edge of what physics allows that they force us to question whether we truly understand the fundamental limits of reality. Their very existence suggests that the universe is far more permissive of extreme conditions than our theories initially predicted. The study of how neutron stars maintain their impossible rotation rates reveals that nature has access to engineering principles that operate through the coordinated manipulation of space, time, matter, and energy simultaneously. This cosmic engineering demonstrates problem-solving approaches that integrate multiple physical domains into unified solutions, an approach that could revolutionize human technology and our understanding of complex systems. Perhaps most profoundly, neutron stars demonstrate that the universe contains structures that exist at the absolute limits of what reality allows while maintaining perfect stability for millions of years. This combination of extremity and longevity suggests that the cosmos possesses an intrinsic tendency toward creating stable complexity, even under the most challenging conditions imaginable. The implications extend to our understanding of life and consciousness. If the universe can create and maintain structures as impossible and sophisticated as rapidly rotating neutron stars, it suggests that reality has an intrinsic capacity for generating extraordinary complexity and organization. This cosmic creativity may be fundamental to understanding how life and consciousness emerge from physical processes. The neutron stars spinning 700 times per second without breaking apart represent more than just extreme astrophysical objects. They are cosmic demonstrations of possibility, revealing that reality operates according to principles far more sophisticated and creative than we imagined. They suggest that the universe itself is an engineering system of extraordinary capability, constantly creating and maintaining structures that push the boundaries of what existence can achieve. In contemplating these cosmic marvels, we discover that the question of how neutron stars maintain their impossible rotation reveals truths about the fundamental nature of reality itself. The universe has shown us that it can create stable structures under conditions where nothing should be able to exist, using engineering principles that coordinate multiple aspects of physics into unified solutions that exceed our theoretical understanding. These cosmic achievements invite us to expand our conception of what is possible, both in nature and in our own technological endeavors. The neutron stars spinning impossibly fast while holding together perfectly remind us that the universe is far more creative, resilient, and ingenious than we previously imagined, and that we have only begun to discover the extraordinary engineering principles that govern reality at its most extreme limits. Throughout this journey into the heart of the universe's most impossible objects, we've discovered that neutron stars spinning 700 times per second without breaking apart represent far more than just extreme astrophysical phenomena. They embody the ultimate expression of cosmic engineering, revealing that reality itself operates according to principles so sophisticated they challenge our deepest assumptions about what matter, space, and time can achieve when pushed to their absolute limits. We began by witnessing the violent stellar catastrophes that forged these objects, where the collapse of massive stars creates conditions so extreme they transform the very nature of matter itself. In that cosmic furnace, electrons are crushed into protons, empty atomic space vanishes, and ordinary matter becomes something else entirely. Ultra-dense nuclear material held together by forces stronger than anything we encounter in everyday experience. Yet from this apparent destruction emerges objects of extraordinary precision and stability. The nuclear pasta phases in neutron star cores revealed matter organizing itself in geometric patterns that exist nowhere else in the universe. These structures, from gnocchi to spaghetti to lasagna configurations, demonstrate that even when pushed beyond the breaking point of atomic matter, reality discovers new ways to maintain order and coherence. The exotic matter in neutron star cores combines strength billions of times greater than diamond with the flexibility to undergo dynamic phase transitions that automatically adjust to resist whatever forces threaten the star's stability. We explored how Einstein's spacetime becomes architectural material around these objects, where frame dragging effects and temporal shear create additional structural support that supplements the already extraordinary strength of nuclear matter. The realization that rapidly rotating neutron stars literally engineer their local spacetime geometry to enhance their stability reveals cosmic problem-solving capabilities that operate at the deepest levels of physical reality. The quantum mechanical foundations supporting neutron star rotation demonstrated that microscopic physics scales up to influence stellar scale phenomena in ways that blur the traditional boundaries between quantum and classical physics. Degeneracy pressure, exotic particle formation, and macroscopic quantum effects combine to create pressure support mechanisms that resist both gravitational collapse and rotational disruption through purely quantum mechanical principles operating on cosmic scales. Perhaps most remarkably, we discovered how magnetic fields become active participants in neutron star structural mechanics, storing enormous amounts of energy in twisted field configurations that extend far beyond the star's physical surface. These magnetospheric structures function as invisible guy wires that help stabilize rotation rates that would otherwise tear apart any material object, demonstrating electromagnetic engineering on scales that dwarf human technological capabilities. The crystalline crusts of neutron stars revealed nature's mastery of material science, creating substances harder than diamond, yet flexible enough to undergo catastrophic restructuring during glitch events while maintaining overall structural integrity. These cosmic materials exhibit self-healing properties and, stress-responsive phase transitions that automatically strengthen regions experiencing the greatest rotational forces. Through precise pulsar timing observations, we witness these cosmic machines operating with clockwork precision that exceeds our best atomic timekeepers, maintaining stable rotation for millions of years while serving as natural laboratories for testing fundamental physics. The mechanical behavior of pulsars demonstrates engineering principles that coordinate rotation, magnetism, and structure into unified systems of extraordinary sophistication and reliability. As we approached the extreme limits of neutron-star physics, we encountered objects existing so close to their theoretical breakup thresholds that they reveal the absolute boundaries of what matter can endure while maintaining structural cohesion. These cosmic stress tests demonstrate that the universe regularly creates and sustains objects that operate at the very edge of physical possibility while maintaining perfect stability across geological timescales. The temporal architecture surrounding rapidly rotating neutron stars revealed that time itself becomes a structural material, with gravitational time dilation and frame dragging effects contributing directly to rotational stability. This discovery demonstrated that the most extreme objects in the universe access engineering principles that operate through the fundamental fabric of spacetime itself, rather than merely manipulating matter and energy, according to familiar mechanisms. Our exploration of neutron stars as cosmic laboratories revealed that these objects provide irreplaceable windows into extreme physics, testing theories about nuclear matter, quantum mechanics, and general relativity under conditions impossible to recreate artificially. Each observation of neutron star behavior provides data about fundamental physics that expands the boundaries of human knowledge while revealing new mysteries that challenge our theoretical understanding. Looking toward future discoveries, we glimpsed revolutionary observational capabilities that will unlock even deeper secrets about neutron star physics, potentially revealing phenomena that exceed our current theoretical imagination. The cosmic laboratories provided by these objects will continue reshaping our understanding of fundamental physics for generations to come, possibly revealing new physics beyond our current theoretical frameworks. The infinite implications of neutron star physics extend far beyond astrophysics to touch the deepest questions about reality itself. These objects demonstrate that the universe possesses self-organizing principles capable of creating stable structures under conditions where nothing should be able to exist, revealing cosmic engineering capabilities that coordinate multiple physical phenomena into unified solutions of extraordinary sophistication. But perhaps the most profound revelation is that neutron stars exist at all. The fact that matter can be compressed to nuclear density, spun to near light speed, subjected to magnetic fields trillions of times stronger than Earth's, and still maintain perfect structural integrity for millions of years, challenges our most basic assumptions about the limits of material performance. These objects demonstrate that reality is far more permissive of extreme conditions than our theories initially predicted. The precision with which neutron stars approach but never exceed their theoretical limits suggests that the universe contains built-in regulatory mechanisms that prevent total structural breakdown even under the most extreme conditions imaginable. These cosmic governors reveal that reality includes sophisticated feedback systems operating at the deepest physical levels to maintain stability and prevent catastrophic failure. As you continue through your daily life, remember that somewhere in our galaxy, city-sized spheres of matter denser than atomic nuclei are spinning faster than kitchen blenders while maintaining structural integrity through mechanisms that harness nuclear forces, relativistic effects, quantum mechanics, and electromagnetic fields simultaneously. These cosmic achievements remind us that we inhabit a universe far more creative, resourceful, and ingenious than we previously imagined. The neutron stars spinning impossibly fast while holding together perfectly represent nature's ultimate demonstration that the cosmos operates according to engineering principles that far exceed current human technological capabilities. They reveal that the universe itself is a master engineer, constantly creating and maintaining structures that exist at the very limits of what physical laws allow, while achieving stability that endures across cosmic time. When you look up at the night sky, consider that among those distant points of light are objects whose very existence pushes every known physical law to its breaking point, yet somehow achieves perfect balance. They remind us that reality contains possibilities we're only beginning to understand, and that the universe regularly accomplishes feats that exceed our wildest theoretical dreams. The story of how neutron stars spin 700 times per second without breaking apart ultimately reveals that we live in a cosmos of infinite creativity and possibility, where the apparent limitations of matter, space, and time give way to extraordinary achievements that challenge us to expand our understanding of what reality can accomplish when all the laws of physics work together in perfect harmony. If this exploration of cosmic impossibility has expanded your perspective on what the universe can achieve, consider subscribing and giving this video a thumbs up. And check out my deep dive into magnetars, neutron stars with magnetic fields so intense they reshape the very structure of space itself. I think you'll find it equally mind-expanding. The universe has shown us that impossible objects not only exist, but thrive at the very edges of physical possibility, spinning faster than we thought matter could endure while holding together, through cosmic engineering principles that reveal reality to be far stranger and more wonderful than we ever imagined.